Hi guys, this is Mrs. Solmer and I'm going to go through a short tutorial on how to solve Hardy-Weinberg problems. So with Hardy-Weinberg problems, you have two formulas, P plus Q equals 1, and P and Q represent your allele frequencies. So the frequency of the dominant allele is P, and the frequency of the recessive allele is Q. Then you have P squared plus 2PQ plus Q squared equals 1, where P squared represents the homozygous dominant genotype frequency. So what is the frequency, or how common is the homozygous dominant genotype? So big T, big T. 2PQ is the heterozygous. So there's a P and a Q. So that kind of gives you an idea that there are two different letters. That's heterozygous genotype frequency. And then Q squared is going to be your recessive genotype frequency. But as just a little hint, Q squared is also your recessive trait frequency or your recessive phenotype. So phenotype and trait are interchangeable there. So Q squared can be the genotype frequency, but it can also be, it is also equivalent to the frequency of the recessive trait, which will help us a lot. All right, so let's get started. My biggest advice to you is once you've identified your given, which is the hardest part of the problem, because if you identify the given wrong, you're going to miss everything. But once you've identified your given, then always solve for P and Q first and as quickly as you can. So our goal is ultimately to have P and Q, because if you were doing a mathematical algebraic equation and it had x squared plus 2xy plus y squared equals 1, and you wanted to solve that, you would need to know what x and y equals. Well, the same is true here. If I want to know what p squared is, I need to know what p is. And if I want to know what q squared is, I have to know what q is. So my ultimate goal is to get p and q first. So the first box that I have here is the very basic type of problem. So if you're given a P value in your problem statement or a Q value in your statement, it's very easy to find the other one because P and Q have to add up to 1. So the first statement says, what is Q if P equals 0.6? Well, Q and P have to add up to 1, so Q has to be 0.4. Now, here's the catch, guys. You can just do 1 minus P if you're bad at math, and break out that calculator if you want. I'm not opposed to using calculators on this. Obviously, you're going to need them. All right. The next problem says, what is P if Q equals 0.8? Well, again, P plus Q have to equal 1. So 0.8 to get up to 1, P has to be 0.2, or 1 minus 0.8 is 0.2. So that's the really, the very quick and easy. If you're given a P, find the Q. If you're given a Q, find the P. But you're not always going to be given the P or Q value. Sometimes you'll be given P squared or your Q squared value. So again, if you're given P squared or Q squared, you're still going to try to find P and Q first. So down here, it shows you how to find P and Q given P squared and Q squared. P is equal to the square root of P squared. So if I know what my P squared value is, I take the square root of it, and that will tell me what P is. So here's an example. If P squared is 0.36, how do I find P? Well, I take the square root of 0.36, and that gives me 0.6, which is my P value. Now, with that P value, I can then very quickly find my Q value, and so Q is 0.4. So again, find your P or your Q as quickly as possible. All right, the next one, it says, what is P if Q squared is 0.64? And I will tell you, 80% of the time, you're going to be given a Q squared value. So the first thing you want to do is find Q. So Q is the square root of Q squared, so the square root of 0.64, and that's going to give you 0.8. Now that you know Q, you can find P. P is 0.2. So again, the first thing you always want to do is find your P and Q value if you haven't been given them. So once you have your P and Q value, you can solve for P squared, Q squared, and 2PQ using those variables as little formulas. So for instance, if P is 0.2, what is P squared? Well, literally put 0.2 squared into your calculator because P is 0.2. We square it, and that will give me 0.04 as my P squared value. So if I'm thinking through this, that means about 4% of my population has the homozygous dominant frequency. Same thing is true to find Q squared. So if I know what Q is 0.8 because P was 0.2. So if Q is 0.8, then I can just square that. 0.8 squared gives me 0.64, which tells me that 64% of the population has the homozygous recessive genotype or the recessive trait. And then lastly, 2PQ. 2PQ is probably the most confusing one for a lot of students, and it shouldn't confuse you. This is just a little formula. So if I know my P value and I know my Q value, I just input them into this little formula. So I do 2 times 0.2, which is my P, times 0.8, which is my Q, and that gives me 0.32. So 32% of my population is heterozygous. Now, if I wanted to know dominant, like Q squared was the recessive trait and the recessive genotype. But the dominant trait is a little different. To know the dominant trait, you have to add P squared, which is the homozygous dominant genotype, but you have to add it to the heterozygous to know the total number of organisms with the dominant trait, because the heterozygous also has the dominant trait. If you're heterozygous, you have the dominant trait. So in this case, if I wanted to know my dominant trait frequency, it would be 0.32 plus 0.04, which would give me 0.36. My recessive trait frequency is just equal to the recessive genotype frequency, or Q squared, so 0.64. All right. So we're going to go ahead and do another practice problem. Remember, at any point, if you feel like, oh, I've got this, you can stop, but I've got 4 different practice problems to go through with you here. All right, so in this problem, it says a certain population has a dominant allele frequency of 0.5. So that tells me my p-value is 0.5. So right away, I can fill that in to my my chart here. So P equals 0.5, my dominant allele frequency. So with my dominant allele frequency being 0.5, I know my recessive allele frequency, which is Q, also has to be 0.5 because these two have to add up to 0, or sorry, not to 0, to 1. So then I use my P to find P squared. So 0.5 squared gives me 0.25. That's my P squared. My Q squared is Q, 0.5 squared, so 0.25. And lastly, 2PQ. So 2 times 0.5 times 0.5 actually gives you 0.5. Decimals are funny. So I've solved for all of my frequencies of Hardy-Weinberg given my one known. So let's try this again. In the next problem, it says a population of 1,000 cats has 250 recessive cats. Now, this is the recessive trait, but I know the recessive trait has to have the recessive genotype. So what they're actually giving me here is Q squared. So 250 that are recessive divided by 1,000 gives me 0.25 as my Q squared value, the frequency of the recessive genotype. So I can fill that in my chart. Well, now I'm given Q squared. Again, I want to find P and Q. So right away, I'm going to go and find my Q value by taking the square root of 0.25. And that's going to give me 0.5 as Q. Well, if I know Q is 0.5, P has to be 0.5. Now I can use my P in P squared. So 0.5 squared gives me 0.25 for P squared. And now I have both P and Q. I can do 2PQ, the heterozygous genotype frequency. And I get 2 times 0.5 times 0.5 equals 0.5. And yes, those numbers are exactly the same. So you see, we went about the same problem essentially, but given a different variable to start with. All right, so I have another problem here. This is a little bit harder, so you might want to just pause the video and try this one on your own on paper if you'd like. Otherwise, I can go through this with you. So in this one, it says a certain population has a recessive allele frequency of 30%. Well, it says allele frequency. So that is my Q value because it is recessive and it is an allele frequency. So they have given me Q is 0.3. So I can fill in the variables in this chart pretty easily. And that's one thing that you need to be able to do, because if a problem is asking you for the homozygous recessive genotype frequency, you need to know that they're asking you for Q squared. And so if you're not able to put the variables with what the actual words are, then you'll get messed up on the problems and it won't even be because of the math. So the homozygous dominant genotype, that would be P squared. The recessive genotype is Q squared. The heterozygous genotype is 2PQ. Notice if it's a genotype, it always has a 2 in it because there are 2 letters in a genotype. And then the allele frequency, the dominant is P, the recessive is Q. So here we go for our problem. The first thing I'm going to do is fill in my Q value because that's what I was given. So now that I know Q, I can find P is equal to 0.7 because P plus Q have to equal 1. So now I can use P and Q to fill out the other 3. So P squared, 0.7 squared gives me 0.49 or 49% or homozygous dominant. Q squared or 0.3 squared gives me 0.09 or 9% of my population is homozygous recessive. And 2PQ, take 2 times your P, which is 0.7, times your Q, which is 0.3, gives you 0.42. All right, now that I have my basic variables, the last thing I need to do is figure out my recessive and dominant trait. Well, the recessive trait is always Q squared. So the recessive trait has to have the recessive genotype, so it has to be Q squared. And so I can look at my Q squared value is 0.09, and that is my Q squared value here. Well, my dominant trait is equal to the other 2 genotypes, P squared plus 2PQ. So you could add P squared 0.49 to 2PQ 0.42, and you will get your total, which would be 0.91. Now, the other thing you can do is 1 minus your recessive trait. So you could do 1 minus 0.09, and that would still give you that 0.91 number. So those are your 2 options to figure out the dominant trait, is either P squared plus 2PQ or 1 minus Q squared. All right, the last situation I can give you, and you'll have to answer questions like this, is if a population has this many people or this many members, how many would have this condition? Well, in this case, it's asking about the recessive trait. So my frequency of the recessive trait, 0.9. To figure this out, I would just take that frequency and multiply it by the number in my population, which in this problem is 10,000. So 0.09 times 10,000 gives me 900. So 900 members of the population would have the recessive trait. All right, I've got one more problem. So if you want to stick around for it, you can keep watching. If you feel like you know what you're doing, you can move on to some of the practice, or you can go through the practice Hardy-Weinberg set number 1 video to check your work. All right, last problem here. It says, in a population of butterflies, the homozygous dominant genotype appears 36% of the time. Okay, so you have your homozygous dominant genotype. So that's going to be your p-squared value. So your p-squared value is equal to 0.36. So I can fill in, again, my variables. You should be able to match your variables to the descriptions. And I can quickly fill in my p-squared value is 0.36 because it was given. So again, find P and Q. So I'm going to quickly find P. P is the square root of P squared. So the square root of 0.36 gives me 0.6. P plus Q equals 1. So I can know my Q is 0.4. Again, once you have your P, find your Q. If you have your Q, find your P. Now I'm going to take this Q value into the Q squared. So 0.4 squared. There's a typo there. Sorry, that should be 0.4 squared. Gives you 0.16. And then 2 times P times Q gives you 0.48. That's your frequency of your heterozygous there. 48% of our population is the heterozygous genotype. All right, so how do I find my dominant recessive trait? Again, remember, start with the recessive trait. It's equal to Q squared. Recessive trait, Q squared. Recessive trait, recessive genotype. They're equal. So once I know this, I can do 1 minus 0.16 to get 0.84. I can also add my P squared and my 2PQ value together. 0.36 plus 0.48 would give you 0.84. All right, last weird question I could give you. It says, after 10 years of equilibrium, how would the frequencies change? Well, after 10 years of equilibrium, I would expect the numbers that we just calculated to be exactly the same. They don't change if you're in equilibrium. All right, so that's what I have for solving Hardy-Weinberg problems. If you have any questions, of course, I'm always available during office hours or advisory. So just send me an email or set up a meet and I'll be able to help you. Have a great rest of your day.